linear regulator experiment, and thank you. So welcome to the Class B amplifier circuit experiment. This Class B amplifier is made from two transistors, one of them being NPN and the other one being PNP. Specifically, it is the BC327 PNP transistor and BC337 NPN transistor. These two transistors in combination form a push-pull configuration. First of all, it has the biasing present over here. These three resistors form the biasing circuit. The purpose of the biasing circuit is basically to slightly turn on the transistor. In Class B configuration, the transistors are basically in the off state until the voltage at the input is large enough. This small biasing does not really turn on the transistors much at all. So what that means is that when the circuit is not doing much, the small amount of biasing consumes a very small amount of power. So if you look at the power consumption of the circuit, as you can see, it is drawing 0.0004 amps. It is drawing about 1 or 2 milliwatts. So the consumption of 1 or 2 milliwatts shows that this circuit is barely on. It is not doing much at all. The small amount of power consumption comes from the small amount of biasing that we have applied onto the base of the transistors. If we increase the voltage to 2 volts where the circuit starts to operate fully, the power consumption increases slightly to 0.0007 amps. So the power consumption has slightly increased while the circuit is fully operating. Let me ramp down the voltage again where the circuit is not operating anymore. So now the power consumption has dropped to 0.0004 or 0005 amps. So the power consumption changes by 2 microamps when the circuit is fully operating. So the small amount of biasing wastes some power, and while the circuit is fully operating, a little bit more power is consumed. So the reading you have to take at the input power is 5 volts at 0.0007 amps. Use that to calculate the power, and then you will get the input power for this circuit. Next, let's look at the voltage at the input. This is the voltage signal going into the amplifier. So we are starting at 200 millivolts peak. So if you look at the oscilloscope, you can see that the circuit is not doing much at all. The yellow waveform is the input and the pink waveform is the output. So right now we are at 1 kilohertz, and at 1 kilohertz with 200 millivolts at the input, the output is completely blank. The reason for this is simply that the amplifier is not able to turn on as the voltage has not exceeded the base threshold. The base threshold is +6 and -6 volts. So unless we have about 1 point something volts, we will not be able to turn on the transistors. So at the moment it is positive 200 millivolts and negative 200 millivolts peak. The positive 200 millivolts and negative 200 millivolts is not sufficient to turn on the transistors at all. So increasing it to 250, then increasing it to 600, 800 peak to peak. Still the transistors have not turned on. As I said, you need +0.6 -0.6 at a bare minimum to turn the transistors on. So that means a peak to peak of about 1.2. So right now we have a peak to peak of 1.1, now 1.2, and you can see small bumps appear. The pink waveform has small bumps appearing into it. So let me do some averaging so it is more easier to see. So we'll do acquire normal averaging. So now you can see small bumps appear on the voltage waveform. This bump is present, this bump is present, this bump is present. These bumps show that the amplifier is starting to turn on. I'll just do erase so just the noise is reduced, or just leave it at normal. So as you can see, the input voltage is 1.2 peak to peak, and the transistors have started to turn on. As I said, you need +0.6 and -0.6 volts to start turning on the transistors. So if I increase the voltage further at the input to, let's say, 1.5, you can see the transistors have partially turned on. Until the voltage reaches their threshold, the transistors will not turn on. So if I take a cursor and measure it, so the voltage at this point where the transistors turn on is no, this type of cursor. I'll set it to Y cursor. The triggering has an issue. Let me enable noise reject for the triggering. So noise reject on. So now the triggering is more stable. Coupling AC, high frequency reject. Okay, so that makes it more. 1 second, 0.30. So the difference between the two voltages is about 0.4. So difference of 0.4 volt shows that you need at least half a volt for the transistors to turn on, and that is the amount of voltage that is being wasted by the transistors. So if I move it down, that is also the amplitude for the output waveform. So the output waveform is 0.4 volts high. The peak to peak voltage is 0.8, but that is considering the losses as well, the losses of the transistor. So if we measure the peak to peak voltage, it is about 0.6. So the input is 1.6 volts and the output is 0.6 volts. So a total of 1 volt is being wasted. That means in this case these transistors have a threshold voltage of 0.5 and minus 0.5. So the NPN transistor turns on at 0.5 volts, the PNP transistor turns on at minus 0.5 volts. So we get a total of 0.6 volt at the output when we have 1.6 volt peak to peak at the input. So if we increase it to 2, the threshold will stay roughly the same. So now the output voltage has changed to the same one as the input. At this point the transistors are able to fully turn on and the output voltage is almost the same as the input voltage. But the transistors are not on at the low voltages. When the voltage is not above the threshold level, the transistors are completely off. So even if we keep on increasing it, this threshold will just stay there. Now the transistor is starting to amplify the voltage. As you can see, the voltages are becoming bigger and bigger. So if we look at the proportional, as we increase the voltage, the gain is increasing. As we decrease it, the distance between the input and output becomes larger and larger. So this amplifier does not perform well at low voltages, but it performs acceptably at higher voltages. The output power you have to calculate using the RMS value. So let's measure the RMS value of the output. So let's go to measure, type, RMS. So the output voltage RMS is 506 millivolts. So using 506 millivolts alongside with the resistor of 1 kilo ohms, you have to calculate using Ohm's law. So Ohm's law is V is equal to IR. So if we bring the camera to the other side, so the Ohm's law is V is equal to IR. The current will be given by V by R. So the voltage is 500 millivolts and the resistance is 1 kilo ohms. So if you use a calculator, so 0.506 divided by the resistance of 1000. We get 0.000506. I is equal to 506 0.506 milliamps. 0.506 milliamps. The power is voltage into current. So the voltage we already know, the current we already know. So we can use that to calculate the power. So the power will be given by 506 into 506 into 10 power minus 3. So let me just perform that calculation. So the calculations are as follows. We use Ohm's law to calculate the current. So Ohm's law is V is equal to IR. V by R will give us the current. So the voltage is 0.506. The resistance is 1000. That gives us a value of 0.506 milliamps. We simply move the 10 power 3 to 10 power minus 3. That gives us in milliamps. Then the power is given by two formulas. Either power is equal to I square R or power is equal to voltage into current. So voltage we already know, it is 506 millivolts or 0.506 volts. 0.506 multiplied by 0.506 multiplied by 10 power minus 3, because it is milliamps, will give us the power. So the power we obtain is 0.256 millivolts. 256 millivolts is the output power. The input power we can measure on the high precision power supply. It gives us 3 millivolts. So 3 millivolts is the input power, 0.256 is the output power. We use the efficiency formula. Efficiency formula is output power by input power. So output power is quite small, input power is quite large. So if we calculate it, we get an efficiency of 8.5%. So this amplifier is 8.5% efficient. So that is it for the Class B amplifier. It is not the most efficient amplifier that is available, but also it is a small signal amplifier. So it is not designed to handle large power. As we saw in the beginning, when the amplifier is off, it is drawing a good amount of quiescent current. That quiescent current is a lot of energy being wasted. So that wasted energy does not do any useful work. Because of that, the efficiency is quite poor. So that is it. Thank you. So welcome to the Class A amplifier circuit. This amplifier circuit has the 2N222 transistor in it. So unlike the previous circuit, which was the Class B circuit, or the next circuit which will be the Class B circuit, this transistor has a good amount of bias applied to the base. So the biasing resistors are the 20K and 3.6K kilo ohm resistors. These form a voltage divider. The voltage divider they form divides the 12 volts at the supply and keeps the transistor in the on position. So if you look at the current draw, it is 0.004 or 0.005 amps if you round it up, and it is drawing 0.05 watts. It is drawing much more power compared to the Class B circuit, because this circuit always needs to draw some power to keep the transistor on. So if I turn off the signal generator, as you can see, the power did not change much at all. The power is still 0.0044. If I turn it on, the power does not change at all, because even when the circuit is doing absolutely nothing, it is drawing a good amount of power. So it is drawing 0.05 watts regardless whether a signal is present or not. So if I zoom out a little bit, I'll show you that. So right now the signal generator is completely off. It is drawing 0.0045. If I turn it on, it is still drawing 0.0045. So the power consumption is not dependent on whether the signal generator is on or not. That means it is not dependent on whether the circuit is doing any amount of work or not. So Class A configuration always will have some amount of power consumption even when it is doing absolutely nothing. So let's look at the waveform next. So this is the waveform for the circuit. As you can see, the input voltage is 10 millivolts and the output voltage is 600 millivolts peak to peak. So 10 millivolts at the input, 600 millivolts at the output, that is a gain of 60. The reason being the resistor at the load is very large. The load resistor is kept as 470 kilo ohms. So 470 kilo ohms is a very large resistance. That large resistance causes the signal to be quite large. If the resistance was kept as a smaller value, it will be a larger load applied to the circuit and then the voltage would be lower. But in this case, as a very large voltage is kept, it is drawing a good amount of, it is generating a good amount of voltage. Next, we will also measure the phase shift. So let me go to measure, source, type. I'll select channel 1 and 2. Channel 1 and then channel 2. I will measure the phase shift between them. So the phase between them is 127 degrees. So it is not exactly 180 degrees, but it is almost reaching that point. So it is about 127 degrees, the phase shift. Then let's look at the power consumption. So the power consumption is given by the output voltage and the resistance. So if we calculate it, we will get